Hello and welcome to our webinar on materials that matter for your research. So today we're going to be looking at materials used in the aerospace and automotive sectors, but of course these materials can see applications in many other areas, which is one of the beauties of material science, that developments in one area can lead to innovation in another also. So hopefully, even if you're not working in aerospace or automotive, there'll be a material that could be of interest to you in your area of research. So before I get into talking about the materials, just a very quick introduction to Goodfellow. We've been supplying materials for over 70 years, science and industry. We have offices and distribution partners around the world to support our customers. And most recently, we've launched a product range of green and sustainable materials to meet modern needs. The main advantages of using Goodfellow materials is that we have a huge range of stocked products available for immediate shipment, but we can also offer custom products so you can get exactly what you need. And all of this is supported by our team of material scientists who are very knowledgeable in their particular areas of expertise. So, on to today's presentation. There's a few different areas that we're going to discuss throughout the presentation. The first one of those is how we differentiate the needs of the many different parts of aerospace and automotive. Clearly, there's in each of these sectors, there's lots of different areas of research and lots of different applications. We're going to look at what materials are commonly used in these areas and how and what properties are important to look at when selecting materials. We're going to be looking at some new and innovative materials, in particular some that are used in the harsh environments that we see in automotive and aerospace, and then some case studies and applications of particular materials, along with new technologies which are overcoming challenges that we see in the development of new technologies. So the first area out of the two areas that we're going to look at is aerospace. So when we talk about aerospace, we need to treat aeronautics, so travel within Earth's gravity, and astronautics, travel within space, a little differently as the environments and challenges are different. As a supplier, a materials life cycle in which the material is being applied. Are we working at the R&D stage, or are we working with an established part and application? You can also see we'll break down into commercial aviation, military aviation, satellites, and spacecraft. There are some recurring themes in what properties are important to each of these, but also equally some differences. So we'll start with commercial aviation. Most airplanes today are made of aluminium, a strong yet lightweight material. Ford Trimotor, the first passenger plane from 1928, was made out of aluminium. And the Boeing 747, a modern plane, is also largely constructed from aluminium. And this goes to show how much aluminium has been the material of choice for as long as we've been making passenger jets. Other metals, such as steel and titanium, are also used in the construction, but in much smaller quantities. Titanium, though also strong and lightweight, is much more costly. And steel is a lot heavier and therefore only used where it's absolutely required, often where high wear resistance or additional strength is needed. On the slide, you can see that we've highlighted aluminium honeycomb. Honeycomb, in general, is a way of having the material in an even lighter form while still offering high strength. It's used extensively in the construction of aircraft cabins and interiors, but also in crash structures of cars and many other applications. Despite the domination of aluminium as the material of choice in modern planes, at the moment we're seeing a trend to use more and more composite materials in their construction. Composite materials, especially those made from glass fibers, carbon fibers, and Kevlar, are widely used in the aircraft industry. They're stronger and lighter than aluminium, and composite materials are so named because they consist of two or more materials that in combination offer increased properties than using those materials individually. So the Airbus A350 frame is over 50% made from carbon fiber reinforced plastic. This reduces the weight of the aircraft and therefore the amount of fuel required for long-haul flights. So this combined with larger, wider wings, together with flaps that follow the flight path direction rather than the wind, combined to create a 25% improvement on the plane's fuel economy, according to Airbus. So we can see here how the combination of engineering and material science can come together to create more sustainable products. The future of innovation in composite materials has also been demonstrated by the Juno UAV, as you can see pictured on the slide. So the Juno uses a graphene-enhanced prepreg, and the 3-meter wide composite-skinned UAV was first revealed at the Futures Day at the 2018 Farnborough Air Show. Using the graphene-enhanced composite, it allows an even stronger and lighter frame. So this again, with strength and lightweight being so important, shows that the direction that composites and aircraft construction might take in the future. But it also leads to some potential new benefits when taking into consideration the high thermal and electrical conductivity of graphene that we'll come to in a moment. So with defence and military aviation, again, aluminium and composites find a lot of use here for the same reasons as in commercial aviation. And there's also some overlap with the materials we'll talk about here back to commercial applications. But with defence applications, there are often higher demands on the materials that are used, as they're used in harsher environments. So we'll start by talking about radar-absorbing materials, which are specific to defence applications. The radar-absorbing materials are used in stealth technologies for concealment of an object from radar detection. Resistive and/or magnetic composite materials are used to reduce the backscattered microwave signals. Innovation in this area may again be driven by graphene, where graphene-enabled electrically switchable radar-absorbing surfaces are being researched and discussed in the Nature article referenced. As you can see in the top left of the slide, the SR-17 Blackbird was a advanced stealth plane that famously leaked jet fuel when it was sitting in the hangar, as they needed to leave large gaps between the panels. This was because the panels would expand so much in flight from the friction generated at supersonic speeds by the air. So this is an extreme case, but having materials with the correct thermal expansion is really important because of the changes in heat experienced by components used in aircraft. This is one of many considerations when choosing a material, but beryllium aluminium alloys have been identified as good for this sort of application, as they have a lower thermal expansion than traditional alloys. Beryllium is also a light metal, so in alloying it in the aluminium, you don't have an increased consideration of weight, which, as we'll see, is a theme that comes up again and again with aviation. In all types of aviation, aircraft must be protected from lightning strikes. At the moment, copper mesh skins are currently being used, but copper is a relatively heavy solution, and again, we're always looking for ways to reduce weight. So as discussed on the previous slide, graphene might be the solution here because of its high electrical conductivity. By incorporating graphene into the body of the aircraft, you could reduce the need for the copper mesh, reducing weight and increasing fuel economy. One last area of materials that are worth discussing here are metal matrix composites. So a little bit different to carbon fiber-based composites. These are a metal sitting in another metal, forming a matrix. So some examples of these include silicon carbide particle reinforced aluminium, which increases wear resistance and toughness. Beryllia particle reinforced beryllium, which provides reduced mass, high thermal conductivity, and a coefficient of thermal expansion in the range of ceramic substrates and semiconductors. So you can match that to the other materials that it's coming in contact with, so they all expand and contract at the same rate. And carbon fiber reinforced aluminium for increased strength and toughness again. And copper tungsten metal matrix composites for their tunable thermal expansion characteristics. So by changing the amount of copper and the ratio of copper and tungsten in the material, you can tune the thermal expansion to the other materials that it's being used with. This takes us on to satellites. So the materials used in satellites brings its own unique challenges from the unique challenges of space. And you will again see some commonality in what's important here, but some key differences. So firstly, I wanted to talk about polyimide films, and in particular Kapton. This is a wide range of films with basic properties of excellent physical, electrical, and mechanical properties, but there are lots of different grades which offer increased properties in different areas. So different grades have better thermal properties, so better thermal conductivity, better electrical properties, improved corrosion resistance, different levels of opacity and transparency, and improved thermoplasticity. So these films are used in a wide range of applications, from capacitors, printed circuit boards, insulation. When you see pictures of spacecraft and they have the silvery orange layer on them, that's Kapton film being used to insulate them from the cold of space. These films are also resistant to radiation, which is another key consideration in space, as the amount of radiation that components are exposed to is increased significantly. So we've talked a lot about aluminium already, and on this slide I wanted to highlight another form, so aluminium foams. Aluminium foams were developed specifically for aerospace, though, as you can imagine, now find applications in many sectors. Again, this is a way that you can reduce the weight of parts while still maintaining high mechanical strength. Copper foams have also been produced alongside aluminium foams, and these are used in heat exchangers due to the high thermal conductivity of copper. However, where aluminium is not suitable, titanium is the next metal of choice. So this is still an extremely lightweight and metal with high mechanical strength, but it's a lot more costly and a lot more expensive than aluminium. So it tends to get used, as I said, in areas where aluminium is not suitable. We're also seeing innovation with additive manufacturing in lots of metals, but titanium being one of them in particular. So one area where you can't use aluminium in spacecraft and the propellant tanks, and there's been lots of advances by 3D printing these propellant tanks out of titanium for satellites and spacecraft. So by using additive manufacturing, you can design parts in different ways, further reducing weight, because the way they're constructed is different from sort of traditional machining techniques. So it's easier to create different shapes that were not possible before additive manufacturing. So again, there's a slight difference between the challenges faced by satellites and spacecraft, though again, some similarities. The one thing that especially is key to space probes is their need to gather data, and therefore have sensors and equipment that can detect this information. So many precious metals and thermocouple wires are used in sensing equipment. And in particular, I wanted to talk about here where platinum wires supplied by Goodfellow were used as a sensor on the Cassini-Huygens spacecraft in its investigation of Saturn. These sensors were used to measure thermal conductivity and thermal diffusivity. And if you're interested in any more on that, then we have case studies on our website that go into a little bit more detail than I've got time to talk about here. Refractory metals are also a class of metals that are used extensively in spacecraft. These are metals that have extraordinarily resistant to heat and wear. They all share some properties, including high melting points above 2000 degrees C, high hardness, and they're chemically inert, though they do have a high density, which does make them very heavy. But the other properties that they have means that sometimes you have to accept that they're going to make your spacecraft a bit heavier. And partly due to the fact that they have a high melting point, refractory metals are also very stable against creep deformation compared to other metals. So the refractory metals or metal alloys of molybdenum, niobium, tantalum, and tungsten have been used in space power systems. These systems are designed to operate at temperatures from 1350 Kelvin to approximately 1900 Kelvin, where the environment they're used in must not react with the metal itself. So often you're creating very high energy states where the refractory metals are very resistant to that. So another material that's been used a lot in space is Maycore. So over 200 distinctly shaped Maycore parts can be found on America's reusable space shuttle orbiter. Retaining rings of Maycore are used at all the hinge points, windows and doors, and also large pieces of Maycore are used in the NASA spaceborne gamma radiation detector. For this application, frame corners are joined by a combination of machined mechanical joints and sealing glass. Maycore has a continuous use temperature up to 800 degrees C and a peak temperature of 1000 degrees. Its coefficient of thermal expansion readily matches most metals and sealing glasses. It's non-wetting, exhibits zero porosity, and unlike ductile materials, so unlike metals, it won't deform. It's an excellent insulator at high voltages, various frequencies, and high temperatures. And when properly baked out, it won't outgas in vacuum environments. So this makes it a very interesting material for many applications, including in space. And it has the added advantage that it can be machined using normal metalworking tools. So prototypes can be made and tested very quickly compared to other ceramic materials. So that brings me to the end of a quick overview of space and materials used in space, and onto some materials used in the automotive industry. So for the purpose of this discussion, we'll be largely talking about materials used for innovation in the automotive industry. So the materials used in high volume manufacture of vehicles are quite well known and often heavily commoditized because of the need to make vehicles affordable. This lends itself a little bit less to Goodfellow's area of expertise and innovative product range, which is why we're going to focus on some of the higher end and more innovative areas of the automotive industry. So motorsport is an area of the automotive industry that is often leading on innovation that is then subsequently applied to road cars. Because of this and their need for competitiveness, they're often the ones experimenting the most with new materials and taking advantage of what material science can offer. So in Formula One, for example, we've already seen the shift from aluminium to using carbon fiber composites, which make up the majority of the chassis and structural components in F1. Some titanium and steel are still used where they have to, but primarily they're using as much composite material as possible. And again, this is because of the high strength and lightweight nature of the carbon fiber and composites that we've talked about before. So one really interesting area and area of innovation at the moment within automotive is battery technology. So lithium-ion batteries have been widely studied because of their rechargeability for obvious reasons. And lithium-ion batteries are commonly used already in portable electronics such as laptops, phones, but electric vehicles are the latest area for us to really try and see if we can take advantage of the technology, and it's pushing the research in lithium-ion batteries. And this is also, I should mention, of interest in many aerospace and military applications. So for a couple of examples, the Nissan Leaf and Tesla Model S currently using lithium-ion batteries as their primary fuel source. And these are production vehicles, as you'll know. So lithium-ion batteries have higher energy densities than lead-acid batteries or nickel metal hydride batteries. It's possible to make the battery size smaller than others while retaining the same storage capacity. Nissan's lithium-ion battery technology uses materials which allow high density of lithium ions to be stored. So again, even within the area of lithium-ion batteries, there's a lot of work to be done to making those more efficient. Lithium-ion batteries have several other advantages compared to other battery technologies. We've already talked about the high energy densities, but they're also comparatively low maintenance and can deliver a large amount of current for high power applications. They also can be made with containing less toxic substances. The downside to battery technology is the weight of the batteries needed to power a vehicle compared to conventional fuel. This is why the research improvements are still needed. And you can see listed on the slide some of the materials. These ones are available from Goodfellow for use in the cathode and electrodes and anodes of lithium-ion batteries. On the next slide, we can see a quick overview of the improvements that have been made so far by the Nissan Leaf. So you can see that by changing the structure of the generations of batteries, you can optimize the storage of the lithium ions and increase the range of the cars. So this area, I think, is one that's going to continue to make progress, and we're going to see lighter, more powerful batteries. Additionally, for electric cars, battery technology is starting to be merged with nanomaterials like carbon nanotubes for better efficiency. So again, the world of material science and nanomaterials is a really important area for battery technology. So this can be used to replace conventional graphite and lithium graphite electrodes in batteries. So ceramics are also used widely in the automotive industry. So there are over 30 distinct applications of ceramics. So piezo ceramics are used in lots of sensing equipment. And you can see a example of how this works. So when force is applied to the piezo ceramic, it produces a voltage, which obviously can be sensed. There's also alumina used in components in control units and fuel pumps. Silicon nitride rollers are used because of their low friction in many cases, and ceramic coatings on engine parts are there to reduce wear and increase efficiency. So one last point on the automotive industry is Goodfellow's involvement in lots of different Formula Student projects. So here is a slide showing the Formula Student project for the University of Lisbon. where Goodfellow have supplied materials in lots of different application areas. So you can see there some of the composite materials used to lightweight the car. Large amount of copper mesh was also used to insulate the car from radio waves, so that the control unit in the car wasn't being interfered with by external radio waves, which is a huge safety consideration. And the relationship in design and material science and collaboration between the team and Goodfellow has been really good to see. So through that collaboration, we've managed to make the motors capable of developing 150 horsepower in a reliable way. And the combination of material science and the students' ingenuity has been able to make this particular Formula Student project very competitive. Okay, so one thing that I just wanted to highlight is that Goodfellow are on YouTube, so it's worth checking out our YouTube channel for videos on different ways to use materials, tutorials, and other content, and we're also available on all the other social media as well. So just to recap, the difference that you'll find from using Goodfellow is that you can save money, reduce from your waste, and get exactly what you need. So I hope that's been useful for you, and look forward to any questions.
Adam, do you want to go through some of the questions that have been posted?
Yeah, sorry, so I'm just looking through. So the first question is, can you tell me about the use of ceramics? So as I mentioned in the slide, ceramics find many uses in both space and automotive applications. So the reason that you would use ceramics is if you want to electrically or thermally insulate. So they're used as lots of spacers, so that two areas are not in contact with each other that are electrically conductive, and where you don't want that electrical or that thermal energy to pass from one component to another. As I said, there are lots and lots of different applications of ceramics within a car. One of the application areas is in spark plugs, where you've got obviously high voltage and high electricity, and you need a ceramic to insulate against that. So another one of the questions here is, what are your product ranges? So Goodfellow's product ranges cover metals, so pure metals, alloys, so metal alloys, and this can be conventional metal alloys or custom alloys that we can make for you. We also have a huge range of polymers, a huge range of ceramics, and compounds and composites materials. The most recent product range that we've added is our range of green and sustainable materials, which are all materials that for different reasons can be used in place of other materials where they might be more sustainable. So here, another question here is some information on the use of graphene coatings for aerospace textile materials for defense applications. So as you can imagine, I can't go into too much detail about defense applications, but as you can imagine, there are lots of uses for textiles, especially with graphene, for the potential of radar absorption in this area. And also materials that could potentially be made by graphene are potentially going to be very strong and lightweight, and the potential of smart fabrics using graphene and other nanomaterials, because of the thermal and electrical properties, is an area that's seeing lots of interest and lots of research. So there's a question here about what will happen if a NOx sensor doesn't work. Unfortunately, that's not an area. I'm not an automotive engineer, but I imagine it's not very good for the car. Modern cars obviously are very reliable, and if the sensor's not working, then the car, I'm sure, will tell you to go and get checked out at the garage. I imagine what will happen nowadays, as cars are obviously full of electronics, is that the car will know that the sensor's not working and direct you to a garage to get that fixed. But obviously, one of the reasons that you pick materials is to make these sensors more and more reliable, so they work 99% of the time. So here's another question: what is the main reason to increase the strength of an aluminium alloy and others? So this really depends on the application. Obviously, if the application demands a high level of mechanical strength, which often is the case in engineering, you want to find ways of increasing that strength. Obviously, mechanical strength is quite simplistic, and there are lots of ways that you want a material to be strong. So it might be sort of tensile properties, but it could be many other reasons as well, which is why you need so many different alloys to cope with the many different application areas. So here's another question. Thank you so much for all of these questions, by the way. It's great to see. I would like to know more on graphene-based structural composites and their use in automotive or aerospace applications. Its current use and benefits compared to other materials in a similar field. So graphene-based structural composites are still quite a new area of research. There are some examples where they're being actually used by Airbus in some real life applications, but a lot of the work at the moment is still in the early stages. So as you see by the UAV that we talked about earlier, and developing those new composites. The benefits are that because of graphene's properties, you can see even increased mechanical properties over using traditional carbon fibers, but also the fact that you can potentially have materials that have a high enough electrical conductivity to do some pretty interesting things. Again, one of those might be to protect planes from lightning strikes and remove the need for that copper mesh. Is there anything else to say to answer that question? I'm sure if any of my other technical colleagues have got different answers to some of your questions, we'll be able to get back to you in some more detail as well. So here's another one. Are you providing metal powders for 3D printing? If yes, will you ship the same to India? Yes, we've got an extensive range of spherical metal powders at the required particle sizes for additive manufacturing applications. And as with all our products, they're available worldwide, so you'll be able to get hold of those in India. One thing to also note is that we're also able to manufacture custom alloys in spherical powders for 3D printing. So if there's a material that you can't see in our catalogue, we can probably provide that as a custom product. Can Goodfellow supply metallic glass sputtering targets? We certainly have met glass in our range. I would need to check specifically to see if we have that in sputtering targets. But if we don't, then we can look at producing those. So that's one that I'll have to just come back to you on the specifics. But obviously it depends on which particular metallic glass that you're interested in as well. There's a question here about providing the PowerPoint. So I think this webinar has been recorded, and we'll also make the slides available after the presentation. So there's another question: can we use PPS multi-wall carbon nanotube blends? I'm not sure if this particular composite has been researched into. I see no reason why you couldn't do some research on it, but that's one we'll have to come back to you on, see if there are any examples of that composite. Just going through the questions now, see if we've got any more. So here's another one: new development in the car industry to reduce air pollution. Obviously, one of the key areas that's been in development for a long time for reducing air pollution are the catalytic converters in cars, which is an area that there's still lots of research into, and an area in particular where advances in nanomaterials could provide further reductions in air pollution. But also we talked about battery technology. So if we're able to all drive around in electric vehicles, then there'll be a huge reduction in air pollution. So the other thing to mention in that area is also hydrogen fuel cells is another area where we may be able to produce electric energy in cars. So it's not just battery technology that we're relying on there. And also as they make all the components of cars more efficient, so whether that's lighter, using lighter composites, again, all these things will combine as lots of small advances to produce a bigger effect. Can we customize aluminium foam for the car industry? Yeah, so as I was talking about before, the aluminium foams were developed specifically for aerospace, but they're obviously not limited to that. So the advance in one sector can lead to advances in other ones. If there are particular applications that you're interested in using aluminium for automotive, then we'd be very interested to talk that through. There's a question here asking about mentioning coating materials used for thermal protection, emissivity, and oxidation resistance. So I'm sure we can answer this in a bit more detail. I can see already one reply from my my colleagues, and yeah, Aphrodite, our technical manager, has already mentioned the use of graphene and carbon coatings for oxidation resistance, because the graphene can form a barrier against the oxygen. But there's lots of other coatings as well. So we've been working with customers on sapphire coatings. So you can take a normal glass component and coat it with sapphire and give it the hardness of sapphire. And really, coatings are an area that are being explored more and more, because they allow you to take potentially a relatively cost-effective material, so maybe a ceramic foam, and coat it with a gold coating or another material that's maybe used in catalysis, and get the properties of a platinum or a gold foam, whilst using a much smaller amount of precious metal, which is a real advantage. I'm sure there are lots of other examples that we could give of the applications of coatings there. So we can be in contact, or please get in contact, and we're happy to talk about more of those if you've got particular application areas. So here's one. We are looking for CM247, CMSX4, IN738 materials as material coupons in a size range. So those are not materials that I'm aware of off the top of my head. Sometimes that does happen with over 70,000 materials, and obviously many more. So that's one we'll have to come back to you on. But certainly the sizes of 25mm coupons are sizes that we're very happy to deal with. So there's a question here on terbium-doped carbon nanotubes. That's one that I'll have to come back to you on because it's not something that I'm aware of. A question here, are you providing shape memory alloys? Yes, we've got shape memory alloys in our catalogue, and we're very happy to talk about applications of those with you. So there's a question here, are carbon nanotubes having a special application during the pandemic situation? So last week, my colleague Aphrodite did a talk on nanomaterials, and one of the areas that I learned about on that webinar was the use of graphene in face masks. So using fabric with graphene in, a company in the UK has been able to develop a face mask which has enhanced filtering capabilities. So that's one area that nanomaterials are being used in the pandemic. Another area is drug delivery. So metal nanomaterials, in particular gold, materials are being used to target particular sites that are affected by the virus. So again, material science will definitely have a role to play there. Again, we've had lots of work to do with lots of companies with polymer materials recently for PPE as well. So I'm just checking through the questions once again to make sure I haven't missed any of your great questions. So there's another question about NOx sensors. Again, I'm not an automotive engineer, so I can't go into too much more detail on that. But again, we'll do a bit of research and maybe come back to you. But I think essentially they're sensors within the engine, which see how much the engine is moving and rattling around. So if there's a lot of movement, maybe something's come loose, and the sensors there are there to see to give you warning that maybe you need to do some service on your engine. Though I could be wrong. But again, we'll come back to you on that one. But essentially, the key there is this piezoelectric ceramic material can be used really effectively as sensors because when it's compressed, it gives off a voltage, and this is down to the structure, the crystal structure of the ceramic, and the movement of the ions within the ceramic. So it's a really interesting material, which gives the applications of sensors not just in cars, but in lots of other areas as well. Sorry, just going through, making sure I haven't missed any of your questions. If I have, or I'm not able to answer them now, as we said before, we will come back to you after the webinar. So I think I've covered all of your questions. So we've still got a few more minutes. If anybody has any more. There's a question or a note at the top here about providing a certificate for webinar attendance. It's not something that I'm aware of us doing, but again, we can come back to you on that. And another one asking if we'll share the PowerPoint, and of course we will after the presentation.
Okay, thanks very much, Adam, thank you all very much for attending. I don't know if someone from Merck just has some final words. If not, I shall close. Firstly, thanks very much, Adam. I think that was a very useful presentation. I did note that through the questions, there were quite a few questions on nanomaterials and coatings. If you missed our webinar last week on nanomaterials, I'm sure if you contact Merck, they will be happy to let you have the PowerPoint slides and recording. It was a very popular presentation, as was this. I think it's also important to note that although this was focused on aerospace and automotive, we, through Merck, we serve a multitude of sectors in India, and we're happy to talk to you. If you have any further questions on either this presentation or materials in general, you can either contact Merck directly, or we have a really highly qualified technical team based in the UK that can be, you can ask them a question via email, and that's technical@goodfellow.com. So if you want to write it down, it's technical@goodfellow.com, and they will respond within a couple of days to your inquiries. So once again, thanks, Adam. Thank you very much for the Merck team, who we work very closely with in India, particularly Rajneesh, Prasad, and Adam for setting this up. And as mentioned earlier, the slides and recording will be available after this event. Rajneesh, I don't know if you've got anything else to say. If not, thank you very much for joining.